All right, good morning. I'll have to quiet down a little bit since I have a mic. Good morning, I'm Bruijn, and
I wanted to introduce you. So it's my pleasure to introduce Ryan Newton from the Indiana University. He is known for his work on DSLs and deterministic parallelism, more verifying determinism, right? And one thing that is special, he came here just for the talk, so he flew in last night at midnight. And he's leaving right after. So we thank him a lot for that.
Well, first I wanted to actually apologize for that, because this seems like a great event. I see all kinds of old friends that I haven't seen in a long time, and a bunch of new faces as well. I would love to have stayed longer. My excuse is that I'm spending all week in Lisbon doing this, watching my son, so that my wife can attend this other event. So that's my excuse, and that's what I'm going to get back to tonight. All right, so as I think Tiark mentioned on the teaser slide in the introduction to the event, these are some of the topics I'm going to cover today. But as usual in any computer science class, we want to try to avoid spending too much time on language syntax or on the details of particular languages. However, in this particular case, we are focused on Haskell, and we are going to cover quite a lot of ground in terms of talking about different Haskell features. But we'll try to, at the same time, keep it focused on concepts, not Haskell peculiarities. This is going to be sort of a broad survey, where rather than going deep on one particular topic and building a single program, we're going to skip across the surface of the rather large Haskell language and talk about a number of different features that make it a good host environment for DSL construction. And so we'll be doing some exercises, some coding exercises. I see all the laptops out. But if you get stuck on any particular one, just wait till we start the next one, because it's not a single deep dive. There will be reset points in the middle as we switch topics. So on that note, the abstract mentioned to Cabal install Accelerate and get GHC and Cabal on your machine. And if you have successfully Cabal installed Accelerate, then you probably have most of the dependencies you'll need for what we're about to do. This I'll need to ask you to do in real time, which is to just grab this GitHub repository that we're going to be working from. This is where the skeletons and the exercises are. So there's actually two branches of interest that we'll be looking at here. So I thought we could just pause for a moment before we dive in and make sure everybody can read this public repository and has Cabal and GHC. Did anyone get an error when they tried to do Cabal install Accelerate?
I know why I get an error, but I'm annoyed by it because I have a choice between Haskell 7.10, 7.6, which is the legacy branch, and 7.4 on an old machine. But I see no way to get 7.8 right now.
Okay. Well, Haskell Platform installs 7.8 right now. That's one of the good options. Okay. But usually when I have separate versions of GHC, I just keep them in completely separate paths and adjust my path to only make one of them visible at a time to keep GHC's brain from exploding. Was that the only problem installing Cabal installing Accelerate? Everyone else Cabal installed Accelerate happily? Awesome. We won't actually directly need the Cabal install Accelerate to complete successfully, as long as you can download this. And then what I want everyone to do once you have this checked out is, as we dive into the next few slides, before the interactive hacking starts, we can hide the latency of typing install all. There's an install all script, or just type make. There's an install all script and a make file at the top of that repository. And that's going to install a whole bunch of stuff, and it might make the room noticeably hotter as everyone's CPU heats up. But we can start that running while we go through slides. So if I could just get a raise of hands, how many people have the Git repo checked out? Git clone. All right, so cloning's working okay. GitHub is up apparently, which is usually the case. Has anyone started install all or make? All right. Did it come up with a build plan? and it's installing a bunch of stuff. So either before or after, do we have a whiteboard over here? Either before or after, sorry, my cords are getting caught here. But either before or after you type that install all, it would be great to switch to a branch called exercises. So the master branch, which you just checked out, has the answers in it. And what we're going to do is we're just going to git check out exercises. And that's the same thing. Install all should still work. All the dependencies are still the same, except there's some holes in it. And what we're going to do is we're going to work on some of those holes together as we dive into the code. OK, so if there aren't any problems to address right off the bat, and everybody's starting to heat up the room.
Yes, I configured Git to check out with Windows line endings, but the install script isn't Win, so it doesn't work.
Ah, yes, yes. OK, the install script is a one-liner.
OK, you can change it?
Yes. You can type cabal install with any of those directories listed in there as an argument, and it will begin the install process. I'm sorry, it reveals my biases that I didn't even think of Windows support, I admit. But you know, that just makes me representative of the Haskell community because our Windows support fluctuates. Simon Peyton-Jones is constantly complaining about it. All right, so I'm going to go ahead, but we can handle problems as they come up. Or perhaps some of the folks that are...
Exercises with an S.
Thank you, thank you. There are a number of dyed-in-the-wool Haskellers in the room that I can see that I recognize. So if you look around you, you might find someone to help with glitches.
There's an error in the make file. It warns me that several packages might be broken on the way. Hash tables and accelerated.
Ah, yes. So you are a Haskell user because you already have packages installed. Is that correct?
No. We had to install Haskell for...
Ah, yes, yes. Okay. Okay, so there's this annoying business about, oh, you're going to break previously installed packages. So there is a approach to this that we've planned for here, which is just run that install all script and give it the argument force reinstalls. So if you give the argument to the script, then it passes it on to that cabal install command, and it makes things happen. It'll just blow away whatever conflicting versions are there and do the install. -- force -- reinstalls. And if any further problem crops up like that during today, that is the go-to solution. Now, we're not messing with sandboxes or anything. We're just polluting your global package environment. Right.
It works now.
Cheerio. OK, so we're going to do a little bit lecture-style conceptual discussion here to start off before digging into the code. I wanted to just frame things a bit for you to show where I'm coming from and how I think about these things. This is exciting because we've got an entire room full of people who are thinking about DSLs. If you're interested in DSL implementation, that means you probably already drank the Kool-Aid with respect to how DSLs are great for combining efficiency and productivity and so on and so forth. So I want to take one particular angle on this and talk a little bit about bundling. So bundling is something we all know in our lives. We all experience and suffer through bundling. This is one instance of bundling. Bundling is when there are some set of things that you want, except you cannot get just those things. Rather, a number of other things are foisted upon you that you perhaps do not want. And this doesn't just come from app ecosystems because of vendor bloatware, also scientific journals like Elsevier, of course, but also closer to home, operating systems represent massive pieces of functionality all tied together in one giant system, and so do general purpose programming languages, right? There's a whole lot of functionality in Haskell or Scala or C++, and it is take it or leave it. You can't have half a Haskell, usually. But there are answers to these things as well. In the OS community, we have unikernels, things like the Mirage project, that are factoring out just the functionality that you need on a particular application and throwing away the rest of the kernel that you don't need. And I would argue that DSLs are basically the approach to unbundling languages and taking just the pieces that you want. And the way I look at it, the DSL project that we're all talking about, that we're all engaged in, has both a negative and a positive component. The negative component being that we want to restrict away language features that we don't want to see, and then we want to build back up domain-specific constructs that we care about. Now, it's implicit in my worldview that we're talking about DSLs designed for high performance. So parallelism, GPU programming, and so on. Of course, the wider world of DSLs covers many, many topics. If we're talking about LaTeX or we're talking about makefiles, then that argument doesn't apply so much. Okay, so let's get a little bit more specific. I mean, what are the things that we want to take in our programming language and what are the things that we want to leave? So we've had a good 10 years of work on what I think of as the modern model of heterogeneous metaprogramming two-stage DSL that has a general purpose host language often with an embedded DSL. And there's a lot of similarity between these systems, irrespective of whether they're embedded in Haskell or embedded in Scala or embedded in C++. Or Python for that matter, spanning the range from Copperhead to ARBB to Delight to Accelerate, a whole bunch of different systems that we're talking about, all have a sort of consensus model to them, which is that they reject a number of expensive language features that are very common in general purpose languages, largely having to do with abstraction and software engineering, things like lambda and virtual method calls and other indirect jumps, dynamic types, dynamic allocation sometimes. My background is in sensor networks, where we programmed very resource-constrained devices, and you cannot assume a malloc implementation, much less a garbage collector. So these are all the things that we want to leave out, but you have that core sort of C or Fortran with statically allocated memory that you want to leave behind, whether you're targeting GPU or an embedded device. With an FPGA, maybe you go even more restrictive and really cut back on what you're allowing. So there's this story that's worked out very well so far over the last 10 years, which is you have a metaprogramming environment. You basically keep all these red things in the meta language, but then you throw them away in the target language. And the beauty of this approach is that the motto abstraction without regret is often used by Tiark and Kunle. And it's a great motto. And I think one of the reasons it works so well is that a lot of these features, like Lambda and other software engineering abstractions, actually work quite well in the meta language. So you sort of get all the abstraction you need for modularity and for software engineering by having these things in the meta language. There are relatively few use cases which cause you to really want them in the target language. Is everything clear in terms of terminology? It's okay if I throw out meta language, target language. We're all sort of on board with the basic DSL picture. So why am I mentioning all this? One of the things I want to talk a bit about today is the concrete ways in which Haskell supports this picture, but also the pieces of the puzzle that I think are less well addressed by current language technology. By current language technology, I mean both the DSL implementations and the host language environments like Scala or Haskell, C++. So I think that the part of this picture that's still immature is fine-grained tracking of which features a particular piece of code is using, so sort of the effect signature, if you will, if you think of these things as effects. And phase polymorphism, where if I write a simple math routines, I should be able to use those at any phase, at any sort of level of generality. I should be able to use it as regular Haskell code. I should be able to use it in a GPU or FPGA. If I use slightly more language features, I should be able to use that piece of code in fewer places. So there are approaches to this kind of tracking. Haskell does it with monads, but I don't know anybody who gives basic Haskell code a type signature with 20 different type classes to track whether or not you use an if, whether or not you use allocation, and so forth. That would be unwieldy, so we need a lighter weight approach if we really want this kind of polymorphism of code across DSLs and across levels, language levels or restriction levels. Actually, I'd be interested to hear some of the feedback on how the Racket community handles portability across languages, since it's a meta language environment. The Delights folks have one paper on this, on interoperability between DSLs, which is interesting. Okay, so that's one of the things that I want you to just be thinking about as we go through the different specific topics we're going to be looking at today. Another general theme for this talk, one thing we need to think about, I guess, is that we've got so many language communities represented here. What is unique to the Haskell one, as opposed to the JRuby one or the Python one, and so on. And one thing I think crops up in a lot of the work that exists in the Haskell community is an emphasis on type safety, on taking type safety as far as possible. So this will crop up in different ways as we go through the different topics of front-end, middle-end, back-end today. So in front-end embeddings, in the host language, we use generalized algebraic data types to represent domain-specific language syntax, and this lets us guarantee that you cannot represent ill-typed programs. So it's impossible for the compiler to ever generate or consume or produce an ill-typed domain-specific language program. And that's a nice benefit. The Accelerate domain-specific compiler is one that we've been working on in my group in collaboration with Manuel Chakravarty in Australia. And it uses this approach not just in the front end, but all the way through the compiler down to LLVM code generation. So it guarantees that it basically can't introduce a type error into the program it's compiling. In the middle end, that's an example of keeping those GADTs while you're transforming and optimizing the program. One of the exercises we're going to do today will in fact be to take a GADT AST and do a fusion optimization on it. So we'll see the extra typing obligations that you have to deal with there as you're effectively discharging small proof obligations when you type check your AST or your AST manipulation code. In the back end, there's some ways that we can get some additional safety with the existing Haskell tools that are out there. We have a culture of using quasi-quotation for generating code. Whenever we spit out C code or CUDA code or OpenCL code, we use these quasi-quotes that are built into the language, and those don't give us type safety, but they do give us a sort of syntax safety, if you will. Rather than munging strings together and doing string append, if you use these quasi-quotes, everything is parsed and guaranteed to be well-structured in terms of syntax in the output code. And going further, I'm going to show you just a peek at some of our LLVM bindings. There's been a Haskell LLVM library for a long time that's provided bindings to LLVM. In fact, the GHC itself uses LLVM as one of its main backends now. But our type-safe wrapper adds an additional level of safety to that, and we've used that to give Accelerate an end-to-end guarantee all the way from source language to generated LLVM. Okay, so that's a theme, type safety. All right. And the examples we're going to be going through are excerpts from many versions, tiny versions of DSLs like Accelerate and Feldspar. And so we don't need to look at the full-blown language because the repository you just checked out has miniature versions of both Accelerate and Feldspar that have been shrunk to be a little more tractable and fit inside that self-contained repository. Well, I say self-contained, but as you can see, there are still a lot of dependencies that are installing for things like pretty printing and testing and what have you. Normal ecosystem stuff. Okay, so I'm going to pause for any questions before going into the first leg of the real technical material here. Questions? All right, let's proceed. Okay, so in this first bit, we're going to talk about front-end features. So that is to say the front end of our DSL compiler. Front end, middle end, back end, this is talking about the compiler that we're building because we're DSL implementers. So in the front end, we have to make choices about whether we're going to be a standalone DSL or an embedded DSL and so on. We're largely talking about embedded DSLs here in this talk. So I'm going to talk about Template Haskell. Template Haskell is an explicit form of quotation and quasi-quotation. That's one option for building a DSL, and you've already seen a little bit of that from the QDSL talk by Cheyenne. So you've seen some Template Haskell syntax already. I'm going to talk about some minor GHC features like Rebindable syntax and the fact that you can disable prelude imports just so you can replace as much of the built-in language as possible. Not quite as much as virtualized Scala, but quite a lot. Finally, there are some other related features. Has anyone heard of observable sharing as an issue with EDSL front ends? Great. So there's been a bunch of work on this. Haskell has what you need to build a good implementation of sharing. And this is basically because EDSL implementations that are staged programs essentially inline too much. A lot of the time in an EDSL program, when you say let x equal f of x in x plus x, because let in Haskell is not overloaded, we don't capture abstract syntax for let. Rather, we construct a DAG, essentially, with two copies of f of x. And we do not want to compile that as f of x plus f of x. I mean, you could if you really trust your common subexpression elimination. But the Accelerate DSL that we're talking about today goes through some effort to recover the graph structure of this so that you avoid significant duplication leading to changes in asymptotic complexity that could be quite unfortunate. All right, let's proceed talking about some of these language features. So the very first thing that probably all of you have seen that we use in almost every strongly typed language that serves as a host language for EDSLs is some form of overloading. So we want plus to do double duty, and we want plus to work over syntax objects as well as over actual numbers. And this works in Haskell via type classes, but it's basically the same overloading approach vis-a-vis DSLs that you see in C++ DSLs like A or BB or Scala DSLs. That same basic idea of overloading operations to work over syntax.
So why do you need overloading if you have a quotation, quasi-quotation?
Good question. So I think of these as two alternative approaches that are... repeat the question. Why do you need overloading if you have quasi-quotation? So there are very different forms of language embedding, and the overloading-based approach doesn't have any quotations. So the Scala LMS talk that you saw yesterday probably had these rep types in it, and it probably lacked any quotation. Is that correct? And this is the same kind of thing we're talking about here. As we bring up some accelerate code, you're going to see exp of int, and you're going to see programs that have no quotation in them, except for the fact that the type includes exp. And there are pros and cons of using explicit quotation versus using overloading. Versus using introspection, because a lot of DSL embeddings just use the native syntax of the host language, but they use some introspection facility to dig up the AST. Template Haskell is somewhat capable of that, but you can always just use your own parser. In Python DSLs, often you'll see people use decorators. So Copperhead says @coup before any function which is meant to run on the GPU. And you don't have to use any other quotation, you just do that. Pros and cons there, and we'll get a little bit more into those pros and cons as we proceed. All right, so rebindable syntax is, I'll just save comment on that to when we bring up a code example showing rebindable syntax. We already mentioned unsafe sharing observation. Our technical approach to this is described in an ICFP 13 paper, and many other authors have talked about it as well. And now we are going to jump over to a code example to look at what rebindable syntax and type classes can do for us. And then we will keep looking as we highlight some areas where they are insufficient. All right, so using someone else's keyboard here. Every Kinesis user reprograms their keyboard in unique ways. It's a form of encrypting your keyboard. All right, so if you go to the overloading directory, this is going to be our first miniature example of, just like the name says, overloading. There we go. I think there are some arrow keys. All right. So this is in the front end directory. We divided things up into front end, middle end, back end, just like in the slides. So if you go into any of these directories with a cabal file, you should be able to type cabal install to get those dependencies. If your install all has already succeeded, then this should go very quickly because you've already installed everything. And in any project directory with a cabal file, you can also type cabal REPL to bring up the interpreter. Or if you want, you can call GHCI directly on these files. Okay, so we've just loaded up this example. Sorry, I'm going to close some of these things. This is the problem with my mirrored approach here. All right, so let's look at what's in here. So the main file, you can, for now, ignore what's in this subdirectory, Feldspar, and just focus on this main file, overloading Feldspar. And let's take a look at this. Oops, I'm sorry. You want to check out the exercises directory. So do as I say, not as I do. And once we check out the exercises directory, is that font big enough, by the way?
No.
Okay, let's make it bigger. Say when. Better?
Okay.
All right. Sorry. Different modifier keys on different keyboards. Okay, so now this if I revert my buffer here, I'll just use my normal keyboard here until I finish reprogramming that one. All right, so if you revert the buffer here, well, you've already peeked at the answers, but we're going to do a little exercise here with rebindable syntax. So what does rebindable syntax do? Well, rebindable syntax essentially makes up for certain limitations of the type class system. We, as Haskellers, know that the type of plus is for any numeric type A to A to A. But the type of if, well, if we put it in a lambda here, if x, then 3 else 4. This is a function on bool. It takes bool as input. Here, that would have been more clear if I just asked for the type. So this is a bool to A, where A is numeric. So why is bool not overloaded? Well, there's been some discussion on this topic, and nobody can lock down a semantics that everyone agrees on for overloading that, so it remains not overloaded. However, at a more basic level, at a syntactic level, we can replace the meaning of if, then, and else by essentially transforming every syntactic occurrence of if, then, else into an application of an if, then, else combinator, which can have any type you want. So this rebindable syntax notion is a way of manually substituting in your own implementations of built-in syntax, like list comprehensions, do notation, and if, then, else notation, before type checking occurs. So you can have alternate types of your own design for operations like if, then, else. As a brief question to the audience, what would this approach do in a call-by-value language? Anybody? So we're going to change if into a function call. Yeah, you'd always evaluate both branches. So the fact that we do this is depending on Haskell being a lazy language. So that's...
No, it doesn't. Come on. If you were going to do it in a call-by-value language, you would just make sure that the second two arguments were thunks, and you would have building thunks be part of your little syntactic sugar.
Right. The fact that we do this without thunking the arguments is because it's a lazy language. But you're right. It's not that other languages could not do it, indeed.
Idris does the same thing. Idris overloads and then make sure that the second and the third arguments are thunks.
Ah, yes. Great. Okay. So anyway...
also, I want to take argument with something that you said. You said this is because of a limitation of type classes. I think another way of putting it is type classes are sane and this is insane.
Ah, okay. Yes. I did not mean to assign any normative value to it. What I meant to say was just that type classes don't overload everything.
I agree. Type classes don't, or at least the way things are built into Haskell, they don't let you do it, and this does let you do it. And so there are alternatives. I agree with that.
Indeed. Yeah, and there's been this movement towards more overloading to support EDSLs. So virtualized Scala overloaded all the remaining constructs in the language that were not overloaded, while loops and so on, converting them into method calls. And this is similar. One thing I can say from the accelerated experience and from some of these other EDSLs is that with respect to indentation and readability, it is quite nice to actually use if then else syntax. Also, simply because of good editor support for indentation when you're using actual if-then-else syntax. So for example, I use structured Haskell mode here, and it has some nice indentation support, and it knows if-then-else in a way that it doesn't know other silly replacements for if-then-else. All right, so let's see, let's proceed. Let's fill in these undefines. So to illustrate how different we can change if from its normal meaning, let's go ahead and use a lambda calculus style encoding of true and false. So let's define true and false to be the procedures lambda xy x and lambda xy y. Okay, so we're going to have to take a look at what this language is. For that, you're going to want to go to Feldspar GADT. And this is actually a mini-Feldspar that Cheyenne and Phil have on their GitHub repository. And we can look at the language. I mentioned we would use many languages, and this indeed is a very, very small language. So we've got lambda abstraction with an explicit type annotation argument here. And you can see our type for types, which is a singleton type, meaning that it's a type with only one value occupying it. And we've got application. So application and abstraction are all that we need to start filling some of these in. All right, does anyone have any of these filled in yet? We have defined booleans here to just work. We don't have polymorphism in our language, so we're just working over int functions. So the type that we're going to give to our lambda to annotate its argument is int. This is not nice syntax because we're writing directly in the abstract syntax of this mini language, but that's okay. So this says lambda x, lambda y. But then sorry, some minor errors introduced in the version with holes. All right, so what do we have going on here? Can someone tell me what to write next here? This is the true one, so we want lambda x, y, x. Well, for that, we need to look at our variable encodings, right? How many people are familiar with de Bruijn indices? All right, some people, but not all. So let's briefly mention how these, this representation of variables work. So probably everybody has written some kind of compiler or syntax manipulating program, more or less. And when you did that, how many people used strings to represent variables? So there are all kinds of different ways to represent binders, symbol tables, strings, what have you. Here we're just using numbers. Why does that work? Because in a lexically scoped program, you can simply look at how many binding forms you have sitting around your current context and count outward from where you're at. So this is variable 0, variable 1, variable 2. Throw away all the names in the program and simply use numbers like 0, 1, or 2. And then in fact, lambda doesn't need to have anything on it. It can just be lambda, lambda, lambda 0 or lambda, lambda, lambda 1. And that is exactly what we're writing here. So we don't use convenient Arabic numerals here for our numbers. Instead, we use this piano encoding where we have 0 to represent 0, and then we have a successor operation that does +1 on our number. And the cool thing about this type of variable is that this is typical of GADT-based abstract syntax in that we have to construct an environment at the type level because we want everything that we need to be statically verified to live at the type level. So this means that we need a type level representation of environments and a type level representation of indices into those environments. So when we type 0 or 0 of suck, then we are constructing both a value and we are constructing a type level index into an environment. So what is the type of this? Well, it's now something that lives in an environment with a B that we skip over, we don't know what that is, and then an A. So this is the numeral 1. And likewise, if we do 2, sorry. Now we are skipping over a B and a B1 and digging out the A. Now, the encoding is this recursive encoding here where we're essentially, you might call this a SNOC list because we're consing onto the end instead of the beginning. So things are a little bit backwards and you have to read this from right to left. So this says B on the front of an environment, which has B1 after it, which has A after it, which has some tail that I don't know. So this could be, this is just talking about the prefix of the environment. It doesn't say we have a stack of 3 things and that's it. It says we have a stack of at least 3 things and I don't know what's after that. Okay, so let's get back to writing our code. All right, so we already wrote lambda, lambda, and we annotated them both with int, saying that the argument to that lambda is an int, and that's because we want to come up with this function, int goes to int goes to int. And in fact, if we put a hole here, and we look at the information present at that hole, we can see that the type of the hole is xp, meaning some piece of abstract syntax, parameterized by an environment, with a return value of type int. So essentially, whatever we type now, better have, whatever we write into this buffer now, better have that type, ending and returning an int. So for example, we could get this to type check by putting an int literal in here. This is just stands for constant. But is that the right program? Probably not. So does anyone have the answer for what we want to put here? So I'll write the combinator on the board here. All right, so we're doing lambda x, y, x is true, and lambda x, y, y is false. So what is the de Bruijn index of x here? Based on the definition we went through over there?
0.
X is actually 1, because it skips over y. Sorry, this is short, lambda x, y is shorthand for lambda x, lambda y in the standard notation. So we have to hop over 1. And hence this becomes 0, and this becomes 1. So what we want to write here in our file is a variable reference. And it can't be 0. That would type check, but that's not the one we want. We want 1. OK, so there's our true. And now what's false going to be? Let's copy paste. What do we change to get false? Don't be shy. Just 0, all right. All right, so now if you go back to GHCI and you reload your program, you can type these things out to see what they look like. There's a little, even in this mini-Feldspar, there's a little pretty printer that will show you abstract syntax rendered like that. So indeed, we see that true is lambda x, lambda y, x, and vice versa for false. Alrighty, so now we're ready to write if then else, right? So we get a Boolean, but in this funny encoding of Booleans, a Boolean is actually a function, right? So how do we implement if? And this is an exotic notion of if. Not only are we not taking a bool, but we're actually taking something that's a function over abstract syntax, or abstract syntax for a function. So I'll just go ahead and fill this in, and you can follow along with me. So we're going to apply B to E1, and then apply the result of that. This is how we apply things to 2 arguments. In our little lambda calculus encoding, things only take 1 argument at a time. So to apply it to 2 arguments, you apply it twice. All right, this thing type checks. But what does it produce? So let's run some test programs here. So this just checks that true and false do what they should. So if true, then x, else 2 times x. X was defined up at the top here as 7. So this should print 7, and this should print 14. So if you run main, you should get 7 and 14, showing that true and false did their thing. All right, so for how many people did main run? Does main run? All right. How many people have an error or something that's stopping them from running main? OK.
It's telling me that true is not in scope.
Lowercase true?
Well, you take true in the REPL, it's telling me it's not in scope.
OK, maybe the module did not load. Was this with Cabal REPL?
What?
So did you get there by going to this directory and doing Cabal REPL?
Yeah.
Oh, I'm sorry. If you do Cabal REPL, that compiles everything, but it doesn't actually bring it into the namespace, which is a little annoying, actually. because it says modules loaded, and you're like, okay, I'm good to go. But actually, you need to do. You've got some tab completion, which helps you out, but you need to do this. We're actually working in a file called. I'm sorry, I may have made a small bug in this Cabal file. Yes, that overloading file is not actually mentioned in the Cabal file. I'm very sorry about that. So if you just type GHCI on that thing, that'll work too. GHCI, overloading Feldspar, then you're in there, and you can type main. And if you're on the master branch, it should just work. Otherwise, if you're on the exercises branch, you'll have to have filled in those pieces of code we just wrote together. All right. So, all right. So how many people, with GHCI of overloading Feldspar, how many people got that main to run? Or if you like, you can just type run GHC overloading Feldspar and see things print out. 7 and 14. Was that a got it to run? Cool. Great. Well, let's proceed. As I mentioned, since we're skipping across the surface here of several different topics, we're going to hop over to another directory and kind of start again. So what have we learned here? Basically, this has showed us how if we want to be able to write programs that look like normal Haskell programs, but actually run some DSL code, then rebindable syntax takes us one little bit further than we've already got via type class-based overloading. And I promised I would mention some limitations of this approach. So in the particular case of Haskell, and a number of other systems as well, there's not really a very good story for data type definitions and for pattern matching. Now, virtualized Scala takes this pretty far, so I believe both of these actually are overloaded in virtualized Scala, although I don't actually understand how the data type definition overloading works, so somebody needs to teach me about that at lunch. But in the Haskell case, we very often build DSLs like Accelerate. They crunch numbers, they apply functions, they have a big library of built-in combinators for chewing on arrays, doing data parallel operations. The same as in Delight, the same as in so many of these other systems. JavaScript River Trail, you name it. Any of these data parallel collection systems. But what they don't do is define a lot of new data types. Now, Accelerate does have some limited support for the user to define their own custom product types. Is everyone familiar with product type versus sum type? Tuples versus union types or case classes? That gives the user some ability to define new product types, and then through some type class instances, teach Accelerate that, hey, not just regular tuples like int, comma, float, comma, character, but also my personal struct is allowed to be a type that's used in the embedded code. So that can add a lot of convenience. Simple stuff like defining a point struct for 3D point cloud application, just to make your program more readable while still operating in the DSL. So that's great, but what about defining sum types? What about defining other sorts of data? What about having the convenience of pattern matching on sum types? So all of that pretty much goes away in Haskell-based DSLs. It happens that DSLs like Accelerate don't need to worry about it so much because you have very little reason to introduce a sum type into a number crunching, matrix manipulating GPU program. But in other domains, that's really not the case. So just for a little thought experiment, I would ask you to consider what it takes to build a DSL for concurrent data structure implementation. So how many people have implemented a concurrent data structure? Like a lock-free hash map or linked list or something like that. So the typical way that you do this is you find some paper in SPA, right? In the Symposium on Parallel Algorithms, where so many of these new algorithms come out, and you read the pseudocode and you type it in. And it happens that the pseudocode is always written in a very tiny, tiny subset of some C Java pseudocode. And you don't really need very many things. So you could imagine having a nice little DSL for writing down that pseudocode for a concurrent data structure, and then getting some benefits. You know, I haven't implemented this, but if we did implement a concurrent data structure DSL, we could write our DSL once instead of porting it laboriously from C++ to Java to Haskell and so on. They're very error-prone codes. They're unfortunate to port. It would be nice if we could have one spec and then run it in all kinds of places, and also maybe generate model checker code and fuzz test those data structures as well for interleavings, scheduling interleavings that you didn't reason about, or missing memory barriers or what have you. So all that would be great, but what would we need to build that DSL? Well, we would need to be able to define data types. If you think about a linked list, you define linked lists to be nil or cons. Same is true with a lock-free like Michael Scott queue, for example. And so you need sum types. That list data structure is a sum type. And you need a little bit of other data. You need mutable locations to do compare and swap on, and mutable arrays of mutable locations as well. And then you need some basic operations for reading and writing memory. Notably, you need to bind recursive functions. So in Accelerate, we never bind recursive functions. Everything inlines at metaprogram time, and you generate some big block of GPU code. But code that traverses some linked list is going to be a recursive function. So you need to actually be able to capture and generate code for recursive functions. So these are all of the things that Accelerate, and I think possibly Delight as well, doesn't do, and could do better. So if we wanted to build this DSL, what would we use? We could do it in Haskell. I just would not suggest the overloading approach. I think if we have this set of features, because we can't overload data type definition, we want to go a different direction. And that different direction is Template Haskell or something like it. So this is where we come back to overloading versus somehow capturing syntax or introspecting on syntax. So there's at least one paper on using Template Haskell for DSL purposes. In this particular case, that was just a paper about making things easier for the DSL author when your target is Haskell code. So Template Haskell makes it easier to expand into Haskell code than actually generating Haskell as a string. Yes, like Lisp, of course. But I think the more compelling case is what we just mentioned on the previous slide, which is handling data declarations. When you want to capture a data declaration and use it in your domain-specific compiler. So let's see what that should look like. Now we're going to do the tiniest Template Haskell tutorial ever. Wait, so how many people have written Haskell code before? I didn't get a full breakdown. How many people have used Template Haskell? All right, it's not a real heavily used feature, actually.
Ryan, that's not only the fact that we need all these data types. Even for the if case, we are overwriting, we are not overloading. So once we have if fixed to use in a special language, we cannot use it in the host and the object entry at the same time. So
right.
For example, as a power function that requires if at the host level and at the object level, then we should use different symbol, and we cannot use the if then else inside that language.
Right, so I will repeat the comment for the microphone's benefit. So the point made there was that there was a limitation that I forgot to mention of the rebindable syntax approach, which is the following. So the nice thing about that overloading of plus is that it composes with other overloadings of plus. If you have DSL1 that defines exp1 and DSL2 that defines exp2, these things can both happily be instances of num, and you can use plus in the same module operating in both of these different types. That hack we did where we replaced if, well, that means that this one DSL is completely captured if. So we can't use it for another DSL, and we can't use it for the host language. So as soon as you start to go down that road, you really get into a space where you want to have a separate module for DSL code. You don't want to have a big module that's mixing a bunch of general purpose code with a bunch of DSL code. You really want to have isolated modules with their own, which have rebindable syntax turned on. I think that's often worth it for languages like Accelerate. Our experience has been when we port large HPC apps like Lulesh, for example, which we ported recently. You're writing a lot of code. It's worth having separate modules, not just for rebindable syntax, but also for the simple issue of whether or not you clobber other aspects of the namespace. So namespace management is this little annoying detail of DSL work that we do have to deal with. So for example, since less than is not overloaded, related to bools not being overloaded, do you use less than in your DSL and simply require that you do some module importing prefixes to keep it from colliding with the normal less than? Or do you start to play this game of naming everything less than star and so on? This comes down to taste, I think. I personally like clobbering the normal names and just having a separate module where you can create a little playground for the DSL. All right, so hopping back to Template Haskell. So with Template Haskell, we would not have that disadvantage of rebindable syntax. We could have completely separate environments or even completely separate syntaxes for different quotations, because Template Haskell segues into the full quasi-quotation feature, which we'll talk about a little bit at the end of our session today when we get to the back-end stuff. Quasi-quotation is like Template Haskell, except with arbitrary syntax, with arbitrary parsers. And I think you already got a taste of this yesterday in Racket, because Racket is a language that not only has a great macro system, but also has the ability to build custom parsers and still leverage all that stuff. And I think you did that yesterday, build a custom parser for a hashlang, mylang in Racket. Is Matthew here today? Oh, okay. All right, so I promised a tiny Template Haskell tutorial. So for this, we want to go to lang features rather than front end. And we want to go to Template Haskell. So this is just a tiny, tiny example of how to use Template Haskell if you've never used it before. So we had several people here who had used Haskell but had not used Template Haskell. So here's Template Haskell. The simplest thing you can do with Template Haskell is construct a quotation. So this thing, if we deleted the quotes around it, it would have type number to, oh, well, actually anything showable to string. But when we put quotes around it, now it's got this type that basically says it's not a function, it's instead an expression. So this is a different exp than the one we were talking about a minute ago with our DSL. So exps are going to crop up in several places, and we'll have to remember that they're separate. But you'll notice that this doesn't have any particular type. It doesn't say that this is a exp of int or exp of function type. It's just exp. So this is an untyped quotation. Now, we can also turn this into quasi-quotation. How many people are familiar with quasi-quotation in some form? Quasi-quotation is kind of everywhere. It came from Lisp, but now is sort of everywhere. So this means that you can not only create quotes, but then you can unquote inside the quote. So if we wanted to splice in something bound to a variable in the meta language, then we could do that. All right, so very recently, Haskell has added a new layer to Template Haskell, which has typed quotations as well as untyped ones. So if we simply add more brackets, I know this gets quite punctuation heavy. There's a proposal to use a Unicode symbol alternatively as an alternative to this doubled up one. But in any case, tolerating it for now. If we do this instead, well, now we have a quoted piece of syntax, and it builds an abstract syntax tree for it, for the full Haskell code, not for some little DSL that we've defined, but rather for the full Haskell syntax tree. And it also gives it a type. So we can be guaranteed that once we splice this in somewhere to generate code, that it will generate an expression which type checks and which has the type int. So that constrains how we use it. How many people are familiar with meta-ML? So meta-ML did a lot of work to develop this idea of typed quotations. Of course, quasi-quotation was around forever in Lisp and Scheme, but typed quotations and maintaining this guarantee, does anyone know, can anyone articulate the guarantee that meta-ML gives you?
So the program generated is well typed?
Yes, if you type the meta program, then every program generated from it will be well typed. So even if it goes on running and generates millions and millions of programs, they'll all be well typed. So that's this rather amazing property that type checking the meta program type checks all the generated code. And this is something that I don't know exactly how many programmers there are who spend time writing programs in Java or programs in some other language that paste strings together to build SQL queries, but I imagine it is quite a few programmers. And none of them get that guarantee, right? When you paste strings together and send it to your SQL engine, you might generate garbage SQL. Much less syntactically it doesn't guarantee syntactic well-formedness, much less type checking. Whereas the meta-ML style quotations guarantee both. Not only will this always produce parsable correct code in Haskell, it will always produce type correct code. And I get all that just by type checking this program here that you see before you, which is a great property to have. Can anyone think of a question?
Yeah, so what about open term?
Ah.
Is it as powerful as meta-OCaml?
No, I don't think so. Yeah. But I was going to mention another limitation. So what would you say is a big limitation of meta-ML as a whole and meta-OCaml, which pertains to our concurrent data structure DSL, or hypothetical? Well, this kind of type quotation only works for expressions, but languages just don't have just expressions. So there's sort of a known limitation of the meta-ML style approach that you don't get to have type quotations for data declarations or for other kinds of constructs, function declarations, data declarations, and so on. Of course, it's not really clear what that would mean because this is the type of the return value, and only expressions have a return value. But it remains the case that we, in the scenario that in our motivating scenario of a concurrent data structure DSL, we indeed do want quotations with declarations in them, with data declarations. Okay, so let's wrap this up and look at our other Template Haskell 2 file in here. There's an unfortunate limitation where those quotations cannot be used in the same file as they are defined. There's some staging restrictions here. So we define them in Template Haskell 1 and we use them in Template Haskell 2. And if you want to run it, all you need to do is hop over to the right directory and just pop it into GHCI. And now you've got access to all these definitions here. And this just shows, once you've got one of those quotations, something of type QEXP, how do you splice it back into the program? So here we just do a single $sign splice, and that generates code at compile time, pops it in there, and then of course subsequently gets type checked. So even when using untyped template Haskell, we can never get an ill-typed program through the subsequent Haskell compiler. But it does mean we might get weird compile time errors that come from the generated code. In this case, the generated code does type check and has type int to string, so we're all good. In the case of the type splice, just like we used double bars, we use double $signs to splice in something that's typed. So this would only allow us to do this at all. It would only begin to expand this if we've given it something of type int. And there's a little bit of a different phasing story with these happening inside the type checker pass, and these happening in a different phase. All right, so those are some just tiny examples of how to create quotes and then splice in quotes. And you can very easily imagine how later, well, let's run our main function just to make sure it works. Yay, we get 6 because we've used both of our spliced in pieces of syntax and applied one to the other, and that gives us 6. Okay, 3 plus 3 and then show, which gives the string 6. So the quotes that we already saw, we're going to modify these only very slightly to say that it's a custom quasi-quote. So basically this syntax by itself says I'm a Haskell quote. This syntax says I'm some special quote of kind foo, and invoke a special parser and do whatever you like inside this block. So that's the capability we'll see later on with quasi-quoting. But just leave that there for now and remember it. All right, so we saw a little bit of Template Haskell. And there's one more demo file we're going to do here while we're discussing Template Haskell. So if you hop back to the front end directory, we just saw Template Haskell, but only for expression quotes. And I promised you data declaration quotes. So let's go a little further. So hop into this Directive-driven directory. And this directory serves 2 purposes. We're going to see Template Haskell quotes of entire declarations. But we're also going to talk about an approach which is often viewed as an alternative to the DSL approach, which is the directive approach. All right, so you can do GHCI or run GHC on the file in this directory and get some output. And now let's look at what that code is actually doing. All right, so there's some comments in here that you can read offline if you want, if you're playing with this repository after we finish up today. But basically, the DSL approach is very popular in the functional languages community and in parts of the non-functional languages community. But an approach that is extremely popular in the HPC community is what's called directive-based acceleration and parallelization. So OpenMP, OpenACC are examples of this. Basically, I want to leave my C++ code alone, and I want to put annotations on the loops that tell it this loop needs to go to the GPU. So in many ways, this is an alternative to the DSL approach, because rather than focusing on designing a custom language for the abstractions in the domain of interest, be it machine learning, graph processing, what have you, rather than doing that, we just want to keep the code in the same general purpose language, but put a little annotation on it. However, I think that this approach is not really as orthogonal to DSLs as perhaps some people might think, because as soon as you have that directive-driven approach to annotating a source program and then expecting a piece of it to run on the GPU, you have to immediately ask the question, well, what are the boundary conditions of that thing? What am I allowed to run on the GPU and what am I not? I doubt that, don't use these extensively, but I doubt that any system on Earth allows you to run arbitrary standard C++ code on the GPU. So there must be some limitation. And the question is, how clearly are those limitations articulated to the programmer, conveyed in error messages, and so on? With a DSL, it's usually crystal clear. This is a custom language. I say what's in it. Anything that I don't say is in it is out of it. With these general purpose languages plus annotations, it can be murkier. And I would urge you all, as perusers of DSL implementations as well as DSL literature, to always kick the tires. So download those DSL implementations, try to do something perverse that the author wasn't thinking of, and see how quickly it breaks. And with most DSL implementations, they will break extremely quickly. For example, I hate to name names, but Streamit, if you download Streamit, you can break that thing pretty quickly. They have some notion of metaprogramming and things that are available at compile time, but it's fuzzy, and the compiler basically works on a set of example programs, but doesn't really have a strict definition for what should and shouldn't happen at compile time. All right, so we want to avoid that kind of stuff. But this notion of annotating programs while leaving the programs otherwise valid in their host language is an interesting idea. So in this little file here, let's just do a thought experiment and think about what would this annotation-based approach mean in Haskell. So I started off with this motivation of talking about unbundling languages. I want my Haskell a la carte. So let's talk about what that might look like. So let's say we have some library of annotations, and let's say we can take our regular old Haskell functions, leave them otherwise alone, no change in their type, no change in their syntax. Here's a double-to-double function, which I would expect to be able to run just about anywhere because it doesn't need to allocate or do anything special. This can run on my GPU, it can run anywhere. So let's say I put a source annotation on it, and I say, foo is annotated, I expect it to be able to run on GPU and embedded, where embedded is some tiny memory platform with no dynamic allocation. GPU is getting so powerful you can do almost anything on the GPU, virtual function calls, whatever you want. But the hypothetical here would be that, this isn't implemented, but the hypothetical here would be that our tool is now going to capture the definition of foo and check foo against these assertions to make sure that foo is actually compliant with our rigorous definition of what can run on these different platforms. So this comes back to that issue that I mentioned of tracking exactly which language features are allowable, which subset is allowable within which DSL, or even which backend of the DSL. Because multi-backend DSLs are not quite as easy as we often picture them to be. We all love to put up a slide that says front end, our super DSL abstract syntax, and then this whole array of backends at the bottom, right? We're going to do GPU, and we're going to do CUDA and OpenCL and FPGA and all this other stuff. But making a full scaled-up implementation of a DSL that targets all those environments and doesn't have any device-specific constructs or ways that you would want to change the program or specialize the program for those different devices, it's hard to imagine that. Because often you do want some degree of specialization for different devices, or some constructs that are available on some devices and not others. So if we move into that world where you expose a little bit of that diversity, then you would want some way to reason about it. All right, so let's pretend this hypothetical annotation works. Unfortunately, we then run into a limitation of modern-day template Haskell. So what we would love to do is to just say, this is a naked declaration or file, just normal Haskell code. We're not going to mess with parsers or anything like that to get that declaration. But we want to just ask Template Haskell to reify it. So Template Haskell has a function called reify, but unfortunately there's this comment in there that the implementation is incomplete, and it's really only useful for reifying type level information. You can reify data structures fine, you can reify the types of expressions, but it's not usable yet for reifying expressions, the right-hand sides of declarations, which is unfortunate. I see you nodding. You've probably run into this. And that comment's 10 years old now. It's been sitting there for a while and hasn't been fixed. Are you shaking your head that I'm wrong, or that that is a sorry state? Yeah, I agree. All right, so anyway, we do have recourse. We can do a number of different things instead. So if we want to capture that definition of foo, perhaps the most straightforward brute force approach is we could always just parse this module, right? There are really good tools available on Hackage for just converting this whole module into abstract syntax and grabbing that definition that we want using the Haskell sourcex package. We've used this to implement a preprocessor recently for our recent paper submission, and it works quite well. You can use a GHC plugin pass. That annotation syntax I mentioned, it's a pretty obscure feature of GHC. I don't think people use it that much, but the great thing about it is that that and thing wasn't just a comment. It was a comment that's recognized by GHC and puts an annotation on the Haskell abstract syntax itself, which then is carried through the compiler. So if you do a compiler plugin, you get to pop into the middle of GHC and somewhere in the middle of its compiler pipeline, and the abstract syntax for this whole module will still have that source annotation on it, and you can do what you need to do. Is that a question in the back, or just adaptation to the extremely warm temperature in here? All right, so option 3 is we could still use Template Haskell. So Template Haskell has this unfortunate limitation, but it doesn't stop you from actually putting your definitions inside a quote. So everything that's inside a quote, Template Haskell can reify the abstract syntax for that perfectly fine. So if we have a data definition that we want to define, we can put it inside some special quote. This is not the same as the quote for expressions. Note, this is the quote for declarations. And we can define new values, and we can define types. And if you run that main function, all you're seeing here is just a little chatter message that verifies that it in fact has captured that stuff. So if we wanted to implement this system, we would take this abstract representation and run with it. Now, one trade-off here is that there are, the comments in this file got mangled a little bit. But there are actually several different levels of complexity to representing Haskell code. So whenever you hear anybody talking about reifying the source representation of a program in a full-blown language, C++, Scala, Haskell, you should immediately question them as to how complex that is. Because for any big language, a full representation of the parse, of what comes out of the parser, is usually pretty big. So for example, Template Haskell has, I lost my numbers in here, but Template Haskell has 22 cases to the sum type for expression. So that is to say data expression equals variable or lambda or 22 cases. That's better than Haskell sourcex, which has 54 cases, because it represents more of the detail of how the actual source looked in the file, which many of those details are not semantically important. But if you wanted to print the code back in exactly the format it was in, you'd need to know all that surface detail. Fortunately, the prolific Richard Eisenberg has implemented a great library called THDSugar, or THDSugar, which strips away some of those irrelevant 22 cases and gets it down to only 9 cases, I believe. So he uses this because the singletons library is a great library, which is a great library for programming at the type level in Haskell. It uses Template Haskell. So when you want to promote a value level function definition to the type level, he doesn't want to deal with all that surface variation in Template Haskell. So first you want to desugar things, get them simple, and then promote them to the type level. And likewise, even if we're not doing something completely different and not promoting declarations to the type level, we could still use that desugar to simplify the representation, and then have a quite nice representation of programs to do metaprogramming with, starting to get back to a little bit of the simplicity of, say, scheme metaprogramming, where programs are very simple.
So what was the argument against the first option?
Well, I believe that the first option does not integrate with build tools as well, because you now need to know where the file is, find it and parse it, and find the name of the thing you wanted and dig it out of the file. The nice thing about Template Haskell is it's language integrated. So all of the logic about when to rebuild your project, all of the GHC staging mechanisms, you get to take advantage of all that. All right. So that is all we wanted to say about Template Haskell and quoted declarations. So anything more to say on that? Any questions about Template Haskell? We're going to come up to our break pretty soon, our coffee break. And let's just close out this section on front ends, and then we'll come back and we'll talk about the middle end and the back end. All right, no questions on Template Haskell? Everyone's going to go use Template Haskell in their next project, maybe? I don't know. My hope today is that something catches your eye that you then are interested in digging deeper in if you're going to use Haskell for a project.
Actually, I do have a question, right? You're telling us about these different techniques, but you've got a lot of experience with them, and you're not telling us so much about that. So where have you found the different techniques you've spoken about this morning useful?
Yes. So I have a lot of experience with the overloading approach. I have to confess, I have no experience with the Template Haskell approach. I have not built a practical DSL with Template Haskell. You guys have. So I'd be interested to hear how it's going. I would look forward to trying it in the future, but I haven't done it yet.
And the third option, annotation-driven?
I haven't done that yet either. Yeah, so that, we only have so many large DSL engineering projects that we invest in, so we haven't tried all the options yet. We notably haven't done it in Accelerate. But they're there and they're options.
So what DSL is in that approach? I don't know if
The annotation-driven approach?
Yes.
I'm more advocating it for future DSLs.
Okay.
Yeah, I can't think of a Haskell DSL offhand. The vast majority of the Haskell DSLs, going back to the 1990s, use this overloading approach, right? They use combinator libraries with a little bit of overloading. PAN, the image processing, DSL, and so on.
Andy have one based on that, Andy Chu? He has this kind of rewriting system on
The Hermit system?
a DSL on top of using Hermit.
Oh, right, the DSL for the sort of tactics, for syntax manipulation.
I'll check that.
Yeah, I don't know very much about it.
Okay.
Although Ryan Scott from his group is joining us in the fall, so I look forward to learning more about it. Okay, so final caveat. This first segment was all about front-end stuff, and I think it's important that we get the front-end stuff right, but I ultimately don't think that these front-end choices that you make for your DSL should, in the ideal world, constrain the fate of your DSL too much. Because I think that most well-engineered DSLs should be able to build multiple front-ends. So that is to say, people talk a lot about the front-ends. You so often hear the argument that, oh, well, we have to build embedded DSLs instead of standalone DSLs because we save the effort of making the parser and the type checker. After working for 15 years or so on DSL implementations, I think those arguments are a little bit spurious because parsers and type checkers are not that hard to make. The big lift, the big engineering lift for something like Delight is the backends and the optimizations. And the front-end stuff doesn't save you from that at all. Sometimes you can leverage some of the optimization machinery of the host language, which is cool. But for the most part, in the same way, programming language theorists don't spend too much time arguing over syntax the way, say, people on Stack Overflow might. We shouldn't worry too much about front-end syntax. We should assume that we can build multiple front-ends for our DSL. That might mean different languages. If you have important core technology in your DSL compiler, it's like an SQL engine, right? We wouldn't say my SQL is only usable from this host language, and you have to implement a different SQL engine if you want to use it from Java instead of C++. That wouldn't make any sense, right? If you have core value inside your DSL, it should be structured as an engine, as a virtual machine, and then you should make front ends for Python and Haskell and Scala and so on. So I'd like to see more separation between DSLs and front ends. And this would also, I think, help get us out of the rut of we're separate language communities, and therefore we have completely disjoint sets of DSLs. We have the Scala DSLs over here and the Haskell DSLs over there, and never the two shall meet. So some of the implementations, I think, have accomplished this. Intel's ARBB had a very nice API, the same way LLVM has a very nice API for constructing syntax. ARBB was a JIT engine with, that's array building blocks. It was an old project that's done now. Copperhead, the re-implementation of it, once Bruijn Catanzaro went to NVIDIA, it was also structured as two separate packages, one for the front end and one for the engine. And Accelerate, we're working on it. So we're working on a Racket front end first, and we also have some demand for a C++ front end. All right, so that's my last comment on front end things. And when we come back from the break, let's address these next two categories. But I'm happy to take any questions before we adjourn. All right. See you in 15? Is it 15?
30.
30, okay. So I guess we'll come back at 11:05.